Go ahead and get started now. So yeah, it's my great pleasure to introduce Liza Brost. Liza and I worked together well, not directly together, but in the same office for several years while I was at Brookhaven, where she still is at. So Liza did her PhD at the University of Oregon on the ATLAS experiment, followed by a postdoc at Northern Illinois University, also on the ATLAS experiment. More recently, so she just finished being a convener of the Higgs and boson searches group for ATLAS. And she was recently awarded the Early Career Award by the DOE. So let's have her tell us all about Higgs.
Thanks a lot, Jennifer. It's delightful to be here today. I wanted to start off by saying that giving talks to this many people still makes me nervous. People keep telling me that I'll grow out of it, it'll go away eventually. I'm still hoping for that to happen. But, so I just want to say I am super excited to be here talking to you guys about this, and I will get through my voice shaking as we go. So, searching for Higgs pair production at the LHC. So, if you're only going to listen to one slide, here's the important one. How do we do that? So we first start by finding one Higgs boson, collect data for 25 years, analyze those data. Why are we doing that? This measurement will give us direct access to the Higgs self-coupling, which gives us a window into electroweak symmetry breaking. So there's your elevator pitch. Now, quickly through where do we start off? We start with the standard model. So the standard model is hugely successful. It describes everything, almost everything that we see in the universe. Everything here in the room today is made up of the latest quarks and leptons. The bosons carry the forces. An interesting fact about the standard model is that the particles have widely different masses, which I've tried to approximate on this slide to scale. But of course, the most important part is the missing piece in the middle. So you've probably all heard our greatest hit from 12 years ago. We discovered the Higgs boson from ATLAS and CMS. Right, so the Higgs boson is the centerpiece of the standard model of particle physics. We believe that it is intimately involved in the electroweak symmetry breaking. The big question here, of course, is the current minimum the true minimum, and thus the universe is stable? Or is there another deeper minimum elsewhere allowing it to decay? The universe might not be stable, the whole thing will end. If this is the case, there's nothing we can do about it, so okay, but it's something that we would like to learn. So how do we do that? I promise this is the extent of the math I'm going to put you through today. I'm an experimentalist. So the theorists tell me that this is the simplest possible way you could draw the potential. We can then expand that potential about its minimum into something that is more friendly to us experimentalists in terms of the Higgs and its mass and couplings. So here, we want to measure the mass of the Higgs. We want to measure the Higgs coupling to itself, both 3 and 4 Higgses at once. So first step, we want to measure the mass of the Higgs. How do we do that? We need a huge particle collider. So the Large Hadron Collider is the largest particle accelerator currently operating. It is 27 kilometers long, and it's located under the French-Swiss border, actually directly under my house in France. This is old. We are currently colliding protons at 13.6 TeV, and it has 2 large general-purpose experiments, ATLAS, where I work, and CMS, where several of your colleagues work. So this is what it looks like from above. I love this picture. Get to live in a beautiful place if you work at the LHC. ATLAS and CMS, the 2 big experiments, are on opposite sides of the ring. Some fun facts for you about the LHC. It has about 1,200 dipole magnets. They're super cold. So again, if this is your off-ramp for this talk, remember that I told you about the huge refrigerator in France underneath my house. Okay. So LHC schedule-wise, from the ATLAS perspective, so what do we care about as an experimentalist working at the LHC? So we've already had 2 runs of the LHC, which we call run 1 and run 2. The big difference between these runs are the center of mass energy. So we started at 7 and 8 TeV, we increased that to 13 TeV for run 2, and with that we increased the pileup, or number of simultaneous collisions per bunch crossing. And you can see what this looks like approximately in the picture. And as you can see, as we progress, it's going to get harder and harder to find whatever process we're looking for in all of that. At the end of run 2, we had collected about 5% of the data that we expect to collect at the entire run of the LHC. And all of the results that I'm going to talk to you about today are performed in that 5% of the LHC data. We are currently in the middle of run 3, so we've increased the energy a little bit more, we've increased the pile up a little bit more. At the end of run 3, we expect to have collected about 10% of the total LHC data set. So as we've all agreed and giggled at the beginning of the talk, the Higgs discovery happened during run 1. I'm hoping, and I'll discuss a little bit in my talk today, that we'll be able to discover Higgs pair production during the HLHC running period, which you can see here at the end. Run 4 plus, really high pile up, really large data set. We'll get to that. So how many Higgses am I talking about here? So I really like this graph because it shows you, first of all, that using the run 1 data set, we were able to discover the Higgs with a couple 100,000 Higgs bosons produced at each of the large experiments. At that same time, we had less than 100 Higgs pair events produced, assuming the standard model is right for how often this should happen. During run 2, we had a couple thousand per experiment, so on and so forth, and you can see how this scales. And this is a log scale on the x-axis. Now, how do we do this? At Atlas, we use the Atlas detector, which is absolutely gigantic. You don't get the idea of the scale here, but this thing is 40 meters long and 20 meters high. It's 100 meters underground, and it has specialized subdetector systems to detect the different kinds of particles. So we'll go through that now. So going from the inside out, we have the inner detector, which we use to detect the tracks of the charged particles. We have the electromagnetic calorimeter, with which we measure the energy of the electromagnetic particles. We have the hadron calorimeter, where we measure the energy of hadrons. And then the muon system, which, you guessed it, measures the momentum of the muons. So I've drawn little sketches for you for what this looks like. So you can see electrons, which are charged and electromagnetic, deposit their energy in the electromagnetic calorimeter and leave a track in the inner detector. Photons, by contrast, are neutral, so we don't have a track associated with the photons. Muons go all the way through. These are relatively easy particles to study. Great, so they get a little check mark. Now, going up one step in difficulty, we have hadronic processes. So we have bottom quarks, which go into the detector, hadronize, and leave what we call jets. Taus, similarly, you can think of these as small jets. In fact, I'm going to refer to the bottom quarks as B jets going forward. The one thing that we can't do is neutrinos. They go right through our detector. We don't see them at all. Now, collecting data, the first step is to trigger on the events that we want to study. So we start with the level 1 trigger, which operates in hardware. The idea is to reject background-like events to reduce the rate from 40 million collisions per second down to a manageable event that we can process in software. So here we're choosing regions of interest in the calorimeter and muon system to investigate further. So basically we have coarse information from the calorimeters and muon system at this stage. We then pass it on to the high-level trigger. So this is software now. We have detailed information, and we have time for complicated algorithms, like doing that tracking that we talked about in the inner detector. So here the idea is to reject the background-like events to get down to about 1 kilohertz. Now, I've been telling you that we need to reject these background-like events. Why is that? This is because the Higgs boson production at the LHC is something like 10 orders of magnitude smaller than the total proton-proton cross-section. So most of the things that are happening when we collide protons, we're not interested in here. We want to find the Higgs, right? So we're able to do that in about 10 total inverse femtobarns of data that were collected during run 1 in 2011 and 2012. And Atlas and CMS announced these jointly. Now, why is this challenging? So unlike other standard model particles, which decay somewhat democratically to various final states, the Higgs boson decays depend on the mass of the particle. So the most common decay is to bottom quarks, and then as you can see, going around the circle down to muons, which I've labeled in purple, but you can't even see, this is a spread of 4 orders of magnitude. Now, maybe somewhat counterintuitively, the channels that we used for the Higgs discovery weren't the most frequently produced ones. And I'm going to show you a little bit about why that is on the next slide. So I really, really like these plots that were produced as part of the Higgs discovery. So you can see, going from left to right, this is Higgs to ZZ, Higgs to gamma gamma, and Higgs to WW. So as the movies progress, we're collecting data in 2011 and then in 2012. And I want to talk a little bit about the way that we display the data that we collect at the LHC experiments. So in general, the colored stacked histograms are the signal and background processes that we're looking for. So this is simulation. This comes from the theorists. The black data points are the data that we collected. So we slowly fill up the histograms as we collect more and more data. We compare the predictions to the data that we've collected. And you can see in all of these cases that as the data comes in, we get a very nice peak in the mass of the 4 leptons in the case of the Higgs to ZZ, get a super nice peak in the mass of the diphoton system for Higgs to gamma gamma. Higgs to WW is more complicated, right? So we don't have enough mass to produce both of the W's on shell, so you get this kind of smeared out peak around the Higgs mass in the case of Higgs to WW. But these 3 channels together were used for the Higgs discovery. We now know the mass of the Higgs boson, and depending on exactly who you ask, it's around 125 GeV. From Atlas, 125.09. So, okay, first step towards measuring the shape of the Higgs potential, we've got the mass. Excellent news. So, once we know that we have found a Higgs, we continue to study it to see if it was the one that we thought we were looking for. So, the one that was predicted by the standard model. Okay, brief aside about the kappa framework. I did promise you very little math, but tiny bit more. Okay. So we have predictions for the cross-section, so sigma, and the decay, so the branching fraction, for Higgs to whatever it's decaying to, are proportional to the square of the effective Higgs boson couplings to the other particles. So that is cross-section times branching ratio, standard model cross-section, standard model branching ratio, times kappa production, kappa decay. And we say kappa regardless of whether this is a resolved loop or an effective modifier. Okay. So we want to see if the Higgs couplings to standard model particles behave in the kappa framework the way that we think they should. So the easiest way to do this is to look at the particle mass, or rather to look at the coupling strength as a function of the particle mass. So if this is a standard model Higgs boson, the coupling should be proportional to the particle's mass. So the coupling of the Higgs to the top should be highest, Higgs to W should be lower, Higgs to BB should be lower. And that's in fact what we see, which is great news. Okay, so far this looks like the standard model Higgs boson. And on the occasion of the Higgs boson's 10th birthday, 2 years ago, we produced a really comprehensive paper on everything that we have learned so far about the Higgs boson's couplings to other particles. So we reported our studies of the couplings to other standard model particles. We've measured the couplings of the heavy fermions and the vector bosons to the Higgs with about 10% and about 5% precision, respectively. We've observed all of the major production modes, and I really like this cartoon from XKCD, which is showing different kinds of scientific papers, and in the bottom left corner, this is very LHC, because we are in fact 3,000 scientists, and this is in fact what we've been up to for the last 10 years. Okay, so back to our efforts to measure the Higgs potential. The next step is to measure this 3-point coupling of the Higgs to itself. Now, in the standard model, this is totally defined. So we know what this should be, right? This just depends on the Higgs mass and the vacuum expectation value. This is very small. So why are we looking for it right now? The theorists have told us that the Higgs pair production in the standard model is super tiny. It's 1,000 times smaller than production of one Higgs boson, and I will tell you right now that the standard model rate is not observable in the current data set. So, okay, very rare, can't get at it right now. We do know that when we do measure it, it will give us direct access to the self-coupling. This is all great, but why am I telling you about it right now with the results from the Run 2 data set? So if we do observe di-Higgs production now, this is a clear sign of new physics. So for example, you could have switched out the Higgs here for some new scalar x. This could happen at a much larger cross-section than standard model. That would be super exciting. The other big challenge that we are facing is that in the standard model, there's destructive interference between the 2 leading order processes involving Higgs pair production. So from the people who named the Large Hadron Collider, I bring you also the box diagram and the triangle diagram. We should probably not be allowed to name things. These two diagrams interfere with each other. So this is showing the cross-section as a function of the di-Higgs mass. So box diagram in blue, triangle diagram in red, and then their interference in green. So you can see overall what we're looking for gets even smaller, so the sum in black. But we can use the fact that we've got these different processes that contribute at different values of Higgs pair mass to hopefully hone in on this process. So if you turn off the self-coupling, so that is kappa lambda, which is the value of this triple Higgs coupling divided by its standard model prediction. So at kappa lambda equals to 0, the only contributions that are left are from the box diagram, right? So you've turned off the triangle diagram. You end up with this black curve, which is shifted upwards, so it's a harder process. You have the maximal destructive interference between the two diagrams at kappa lambda of around 2. So you can see a double peak structure, which hopefully, once we're getting close to that, that's something we can start to look for. And then kappa lambda greater than about 5, the triangle diagram really dominates, and we're shifted down to low Higgs pair mass, much softer kinematics. This is something that we can use in our searches. In addition, if we change the value of the self-coupling, this also has a dramatic effect on the di-Higgs cross-section. So here we're showing the cross-section for different Higgs production modes. Di-Higgs is in black, so you can see moving away from the standard model value, which is the dotted line, the cross-section increases by orders of magnitude. So if the self-coupling is different from the standard model, this is something we could see now. The cross-section is larger, it's more likely to happen. Okay, so back to exactly how we do this. So we talked about all of the different Higgs decay modes. Now we have 2 of them. So you have a lot of different options for searching. In this case, there are 3 that kind of drive our sensitivity. So this is di-Higgs to 4b. This has the largest branching ratio, so about a third of the di-Higgs events. Di-Higgs to BB tau tau. Here you have a trade-off between the large branching ratio to BB and the relative ease with which we can reconstruct the Higgs to tau tau decay. And then di-Higgs to gamma gamma BB, where you benefit from the excellent diphoton mass resolution that we saw during the Higgs discovery videos, and the large branching ratio to Higgs to BB. In all of these searches, we can use the Higgs masses and the 4-body mass as discriminating variables between the signal and the background. Now, depending on the different channel, the resolution of the signal mass peak is going to change a lot. So we saw that in the Higgs to ZZ, Higgs to gamma gamma, Higgs to WW plots. And of course, the relative normalization of the signal and background are going to be different depending on the exact process you're looking for. So I want to tell you about the search that I've been working on. So this is di-Higgs to gamma gamma BB. Some of you, this is not working very well on your projectors. Some of you asked me this morning, is this something that we think that we have seen so far? Yeah. Thank you. That's much better. Okay, so this is a candidate event from the 2017 data. This looks very much like we would expect if there was a di-Higgs to gamma gamma BB event happening in our detector. You've got 2 nice photons, you've got 2 nice B jets. This is very exciting. We can't say for sure exactly where this originated. So, how do we search for di-Higgs production in the gamma gamma BB final state? So, we start by simulating the signal process. So, di-Higgs to gamma gamma BB, you've got 2 photons, 2 B jets. This is very straightforward so far. We produce, in our simulation, di-Higgs production via gluon fusion. So these are the triangle and the box diagrams that we talked about before. We also have some subleading production via vector boson fusion. So here, you've got 2 vector bosons coming in, 2 Higgses coming out. There's 1 diagram that involves the self-coupling, exciting, and 1 diagram that involves a new coupling that we haven't talked about yet, which is the 2 vector bosons and the 2 Higgses. Now, what does the signal look like? I actually realized that we didn't produce a public plot with what the signal looks like in the latest paper, so you'll have to forgive me for using the background as a proxy. But here, you have the continuum background in blue, the total background in pink, and the bump that you see at the Higgs mass is from the resonant background from single Higgs production. So it looks exactly like what the signal would look like. Very nice mass peak. So then we have to simulate the background processes. So this comes from things like just you have 2 photons and 2 B-jets, completely unrelated. You also have backgrounds from misidentified objects. So for example, if it's actually an electron, but we reconstruct it as a photon. So again, thinking about how we reconstruct the particles in the detector, if you lost a track, it would look like a photon. And then we have that resonant background that we were talking about on the last slide, where you have 2 photons coming from the Higgs decay and then 2 unrelated jets. And here's what that looks like. So you can get a relative idea of the kind of background processes that we're dealing with here. So again, in the stacked colored histograms, the blue is the continuum production of photons and jets. And then the yellow are the single Higgs backgrounds. So that's the resonant peak at the Higgs mass. So we want to compare the signal and background predictions, so what those simulations look like, and design an analysis selection. So first, we want to see what kind of events we can actually select using the Atlas detector. So I told you before about how the trigger system works. So here's how we would select diphoton events using the Atlas trigger system. So we start with the hardware trigger. Remember here we have coarse calorimeter information only. Then you can see what it looks like by the software trigger. So calorimeter plus regional tracking. You can see there aren't any tracks associated with the photon candidates. And then of course, offline for reconstruction for analysis, you can see the whole event. And this is a Higgs to gamma gamma event that we selected in the 2020 data. One other special feature about analyses looking for Higgs decays to 2 photons is that we have a special way that we select the primary vertex. And the primary vertex is the collision that we want to study. So remember we talked about pileup before? You have a lot of unrelated collisions happening. You want to find the one that's associated with your process. Now, if you have an event produced that produces a lot of tracks, so if you have lots of jets related to it, this is very straightforward. If you don't have a lot of tracks, so for example, you're studying 2 photons, we have to get a little bit fancier. So we have a neural network that uses input variables, including tracking and photon pointing information to select the appropriate vertex. We then start the event reconstruction from the selected vertex. Okay, so then we design our analysis selections. So we want to select events that have 2 photons with diphoton mass near the Higgs mass and 2 B-tag jets. So here for this analysis, we've used a B-tagging algorithm with 77% efficiency. We apply energy corrections to those B-jets to hopefully sharpen up the resolution of the Higgs to BB peak. We cut on the number of central jets, so that's jets in the central part of the detector, to reject the TTH background. We cut on the number of leptons, so we say we don't want any leptons in these events, to reject the TTH background where the tops decay leptonically. And then we require that the number of B-tag jets is exactly 2 for orthogonality with the other di-Higgs searches. We'll talk about the combination in a bit. We also use the modified Higgs pair mass in this analysis. So here we take the invariant mass of the 2 photons and the 2 B-jets. Then we subtract the diphoton mass, we subtract the di-B mass, and we add 250 GeV. This is effectively saying, we think this event comes from 2 Higgses, let's reconstruct it in that way. So you can see in particular, for resonant di-Higgs production, this sharpens the peak that you're looking for. So these are the 2 blue peaks. Before is dotted, after is the solid line. You can see that it does sculpt your background quite a bit. So the black line is the gamma gamma plus jets background. So that ends up starting at 250 GeV, and it doesn't do very much at all to your standard model di-Higgs signal. So then we split in this modified mass variable above and below 350 GeV. So here we have the simulated di-Higgs signal with different values of the self-coupling. So remember, if we have large values of the self-coupling, everything's going to be shifted low. And then for the where we turn off the self-coupling or at the standard model value, it's going to be shifted higher. So we make 2 different categories. We analyze the data below 350 and above 350, focusing on that BSM signal with large self-coupling at low mass, and then focusing on the standard model at high mass. Okay, so then we want to select events consistently in the data and in the simulation that look like they came from the signal process that we're searching for. So in order to do that, we design a boosted decision tree to separate the signal and the background. Now there's a lot going on in this plot, so we'll go through it a little bit slowly. So the standard model signal that we're looking for is in pink, and you can see that that's peaked at high BDT score for both the low mass and the high mass region. You can see in particular for the low mass region that the signal with the large self-coupling peaks even higher. We design 4 analysis regions at low mass and 3 at high mass in order to get the most possible sensitivity out of this data set. We also consider uncertainties that come from our understanding of the LHC and the Atlas detector from both the reconstruction and the analysis techniques used and from the theoretical predictions. So here's a table of the leading systematic uncertainties in this analysis. You can see that they're all super tiny. So this is the impact in percent on the final result. So going through them from top to bottom, first we consider the photon energy scale. So that is, what if we are reconstructing the diphoton mass slightly lower or slightly higher than it ought to be? We vary this within our expectations of the detector design, and you can see this has a very small impact on the analysis. Same thing with the resolution at the diphoton mass peak. We also assign a systematic uncertainty on the heavy flavor content. So the question here is, how often do single Higgs backgrounds without an actual bottom quark in the matrix element actually contain B-jets? So here we've applied 100% uncertainty to the gluon fusion, the vector boson fusion, and associated production of single Higgs backgrounds to cover this unknown process. Finally, we have an uncertainty on our background model that we call the spurious signal. So this is an uncertainty from the choice of the background fit function. So here, if the fit shape that we chose was different from what the data is actually telling us, you might find a fake signal, so we account for that fact. Okay, so we finally get to the end of the analysis. We've designed a selection. We've simulated the signal and background processes. So we want to either, hopefully, unblind the analysis and see di-Higgs production, or set limits on how often it could have happened in this data set without us noticing. Whoops. So here's what this really looks like. So here you can see that for the least sensitive low mass region and the most sensitive high mass region, I picked these so you can see one with high stats and one with low stats, the comparison between the data, so the black points, and the fit function to those data. So you can see that, unfortunately, this agrees extremely well with our background prediction. So we can move on to set limits. So we set limits on the signal strength. So this is the number of times the standard model prediction of 5 expected, 4 observed at 95% confidence level. We also set limits on the di-Higgs cross-section as a function of the self-coupling and of the 4-point vector boson di-Higgs coupling that we discussed during the signal section. It's interesting to set limits on the cross-section as a function of these variables because then you can compare to the theory prediction. So starting from the self-coupling, on the left, you remember that there was this quadratic dependence on the cross-section. So the line where the limits intersect with the theory prediction is the values of the self-coupling that are still allowed. Same thing for the 4-point coupling. Now, I've told you all about the gamma-gamma BB channel, which was my favorite, but I wanted to put this in context a little bit with the other di-Higgs channels because, of course, we had all of these different ways that you can produce di-Higgs events. I told you that the 3 most sensitive channels were di-Higgs to 4b, di-Higgs to gamma-gamma BB, and di-Higgs to BB tau-tau. So you can see here, these 3 do turn out to be the most sensitive. And we set a combined upper limit of about 2.5 times the standard model prediction from all of these channels combined, which is really exciting. We can also make the same plot for all of the different channels, setting limits on the cross-section as a function of the self-coupling, intersecting with the theory prediction. And we see that the self-coupling can be between negative 1.2 and 7.2 in this data set. So what can we expect for run 3? We've talked a bit about what we were able to achieve during run 2. So we've already seen a factor of almost 2 improvement due to improved reconstruction analysis techniques in the full run 2 data set. The way that I'm getting this number is you can compare We produced a di-Higgs combination in the first quarter of the run 2 data set. You project that forward, just guessing, okay, we have 4 times more data. The analysis should get twice as sensitive. In fact, we ended up beating that by quite a bit. So you do the same thing projecting forward to the run 3 data set. I expect that either with that same level of continued improvement in reconstruction and analysis techniques, or if you combine the work that Atlas and CMS have done together, we're going to be setting limits that are kind of around 1 times the standard model prediction, which is really exciting. The other thing that we have to look forward to is that we have made upgrades to the way that we select events in Atlas in order to do a little bit better. So it's particularly challenging to study these low MHH events in the hadronic channels because of all of the multi-jet background that we are producing at the LHC. You need to be able to reject this. So one of the things that we have done is that we've added new triggers that are specifically targeting di-Higgs to 4b, di-Higgs to bb tau tau. Now, this is, again, a very busy plot, but as a function of the truth di-Higgs mass, you can see the blue dots were the triggers that we had available for the di-Higgs to bb tau tau search during run 2. And this is the efficiency for the different values of the truth di-Higgs mass. So you can see that it's, in fact, not very good for most of this mass range. Now, in run 3, we're increasing that to the pink points. So if you look at the ratio to the run 2 in the bottom panel, you can see that for especially these low values of MHH, which remember we're very excited about because they're characteristic of beyond the standard model values of the self-coupling, we're increasing by more than 50%, which is really exciting. The other big news for run 3 is that we have continued to improve the way that we identify the B-tag jets. So here we're showing different flavor tagging algorithms. So the algorithms that we use to identify the B-jets per year that those algorithms were developed. So here we're comparing to what we had available in run 2. So these are the first 2 points. This is the C-jet rejection on the left axis, the light jet rejection on the right axis, and you can see that we're going up by factors of 4 in both cases for the latest algorithms that we'll have available to analyze the run 3 data, which is really exciting. So now with the rest of the time, I want to talk a little bit about our plan for the HLHC. So as I alluded to in my very first slide describing, what does the LHC look like to Atlas, the pileup is going to get way, way worse. So this is actually a simulated event in the CMS detector. They tell me that this is a Higgs to tau tau event, really hard to tell on top of all of that pileup, right? So this is 200 simultaneous collisions. This environment is going to bring huge challenges for us. So the detectors are going to be irradiated. The detectors are going to be absolutely full of all of this information that's coming in. And of course, the trigger rates are going to be enormous. So we're planning really exciting upgrades for the HLHC. Obviously, going to upgrade the detectors themselves. Both Atlas and CMS are planning exciting upgrades. We need to change the trigger menu and the trigger hardware to be able to cope with this event rate. We're going to have to continue our improvements to the event reconstruction. This is going to be a challenge even for the software and computing, just where do we put all of this information? And of course, we'll need to continue developing innovative physics analysis techniques. So I'm going to talk a little bit about these. So on the Atlas side, we are planning an upgrade to the trigger and data acquisition system that will allow us to select a megahertz in the hardware trigger and 10 kilohertz out of the software trigger. We have improvements to the muon system and trigger. We have a brand new NCAP high granularity timing detector, which will add timing information to the space information that we have already. There will be upgraded electronics for the calorimeters in the muon system and a brand new inner tracker, which is going to be very precise, but also extend our coverage further in the forward direction. So I wanted to talk a little bit about how we make these projections for the HLHC before I show you any of them, because there's a lot of caveats that you need to be aware of. So we start from the published LHC Run 2 results, which is usually what Atlas does. CMS has also produced some results using simulation. We adapt a little bit to the known conditions at the HLHC. So obvious things like you change the center of mass energy from 13 TeV, which is what we had during Run 2, to 14 TeV, which is what it'll be at the HLHC. You can take the change in pileup into account, obviously scale up the data set. You can include some simulation of the detector and reconstruction performance, although this is more complicated. And then you have to make a lot of assumptions about what the theory and experimental systematic uncertainties are going to look like. And we usually present a few different scenarios. So in the plots that I show you in the coming slides, we're going to be comparing the totally unrealistic scenario where we just say, okay, there aren't any systematic uncertainties, we don't care about any of it. So that gives you an upper bound on the possible performance. And then Atlas and CMS have agreed on a common baseline scenario for the systematic uncertainties for the projections. So here we assume that the detector and trigger performance will be comparable to Run 2. So I hope I've already convinced you that that's going to be a challenge right away. We assume that we'll be able to improve the experimental uncertainties with the square scaled down by the square root of luminosity. We have volunteered our theory colleagues to reduce the theoretical uncertainties by 50%. Hopefully that they can keep up with that. And then we assume that the luminosity uncertainty will be 1%. We compared to the scenario where we only volunteer our theory colleagues to improve the theory uncertainties. And then finally, the most pessimistic scenario is that all of the systematics stay like what they are in Run 2. So I wanted to start by showing you what this looks like for the single Higgs couplings. So these should be moving really into the precision regime by the end of the HLHC. Those that are not still dominated by statistical uncertainty will be known at a few percent level. And as you can see, most of them will be dominated by the theory uncertainties. So here we compare the statistical uncertainties for each of the kappas. So these are the couplings of the Higgs to the other standard model particles. The blue lines are the statistical uncertainty, the green lines are the experimental uncertainty, and the red lines are the theory uncertainty. So there are a couple missing here, more difficult to access at the HLHC and therefore more difficult to project. So this includes the Higgs coupling to the charm quarks, Higgs coupling to invisible, so that's things that we can't see in the detector like the neutrinos, and the Higgs self-coupling. So thinking about the future. Every 10 years or so, the particle physics community in the US gets together to brainstorm on the future of our field. Ultimately, at the end of this process, these brainstorms are written up in many, many papers that serve as inputs to recommendations to the Department of Energy. They're the ones that give us money to do this. There's a similar process every few years in Europe, and that will be coming up next year. So I wanted to start by looking back at the previous European strategy update. For this process, we started preparing our inputs in 2018. And at that time, the message was that we will need more than the full HLHC dataset to measure the di-Higgs cross-section. So the Higgs Yellow report from 2018 says that we'll only get to 4 sigma, so remember we're aiming for 5, on the di-Higgs cross-section with the HLHC dataset. And this is combining both Atlas and CMS results. Of course, we now believe that this is conservative. I've shown you that we are beating the projections so far, even just during Run 2. At this point, we also said that the uncertainty on the value of the self-coupling would be 50%. Now, since we know that this is conservative and old, this implies the need for new combined projections for the next European strategy update, which will happen next spring. I wanted to make a direct comparison before we jump into that. So during the time of the previous European strategy update, so 2018 when we were preparing these inputs, we produced a combination of 5 di-Higgs channels, most of which were based on that 1/4 of the Run 2 dataset. We had that 50% precision on the self-coupling, 4 sigma significance on the standard model di-Higgs cross-section, combining both Atlas and CMS. Now, at the time of the last SNOMAS process, we were preparing the inputs 2 years ago. So at that point, Atlas produced a combination of the 3 most sensitive channels, gamma gamma BB, BB tau tau, and 4B. So together, we get to 3.4 sigma on these 3 channels alone, and the self-coupling limits that we were able to reduce were about the same as the Atlas plus CMS combination from 2018. So that gives you an idea of the progress that we're making. Now, we haven't finished the official combination, but we expect from some back of the envelope calculations that we'll be able to get to 5 sigma, just based on the improvements that we've made so far. Now, I want to talk a little bit about how we can make these projections in a way that is convincing to other physicists and to our funding agencies. So one way that we've talked about making this messaging is looking at how we have improved our analysis techniques so far. So we can't say, okay, we're going to be really smart during the HLHC, we're definitely going to get a factor of 2 better. But we can say, looking back, comparing previous searches. So this is from the di-Higgs to BB tau tau projection that was just made public about a month ago. So here we're comparing the expected limit on the signal strength from the partial run 2 result, so that's in orange, to the full run 2 result, so it's the blue dot, as a function of the integrated luminosity. So you can see if you just project forward that earlier run 2 result, you only get to the end of the orange line. But in fact, when we analyzed that much data, we actually came to the blue dot. And then we decided last year that we could in fact do better on this data set. We could push harder on this. So we published this 3rd paper, same data set, same channel. You can see that the limit on the signal strength gets a little bit better. And we show if you project forward that blue point, that we've effectively earned or gained 60 inverse femtobarns of data for free. And that's as much data as we collected in the last 2 years during run 3. So this is a big deal. The other thing that we can do is we can try to include those improvements that we've made on object reconstruction. So I was telling you that we have already improved the way that we identify B-jets at ATLAS during run 3. So if we want to include that information in the projections for the HLHC, like we already know that we're getting better at this, we can use this plot on the right to discuss something like that. So this shows the significance, so the discovery significance for di-Higgs in the BB tau tau channel as a function of our efficiency of reconstructing B-jets at the C and light jet rejection point that we used during run 2. So you can see the significance gets worse. If our B-tagging efficiency gets worse, the significance gets better. If our B-tagging efficiency gets better, this is fine. Now, I told you that we used the 77% working point during run 2. If you instead increase to an 82% working point with that same background rejection, this we see as the actual performance for the latest algorithm. So this isn't some fantasy that we're able to have the higher efficiency for the same background rejection. So that's really cool to see that we're matching these curves. Okay, and then I wanted to wrap up with a bit of a historical perspective. And it is my, my dear hope that I write a paper like this someday that somebody can point back at and be like, we totally outstripped that. So this is a quote from the ATLAS technical design report. So this is when people had proposed to build the ATLAS detector about our possibilities of observing the Higgs decay to bottom quarks. So here we've said the only way you can possibly do that is in association with a W or Z boson or with a top-anti-top pair. I've also dug up some quotes on studies of Higgs pair production. So this is from some theory buddies about 10 years ago. So in total, di-Higgs production with a decay to 4 B quarks is terrible. It is too bad to be a suitable search channel. Similarly, 20 years ago, it is essentially impossible to determine the Higgs boson self-coupling in proton collisions to 4B. And again, we've seen that 4B has been useful already in the di-Higgs searches. And then finally, from previous ATLAS projections for the HLHC, we said that we were getting started on studying Higgs pair production at the HLHC. The measurement is very challenging, but is nevertheless anticipated to be accessible at some level. And of course, we've seen measurements of Higgs to BB. We've seen that di-Higgs to 4B is one of the leading channels, contributing to both the cross-section and self-coupling combinations. So yeah, I leave you with the question about the Higgs potential. We still need to make this measurement. We have a plan to make this measurement. It is going to be very challenging. but this should keep us busy for the next 20 years. So I think I have shared with you that the HLHC will bring new challenges for these studies. The Atlas detector upgrades plan to maintain or improve upon the current performance. I've showed you some examples of the creativity that we've already put into the reconstruction and analysis techniques. So we've improved upon our previous rounds of Higgs projections. So the question is, what can we do in the next 20 years? And I leave you with this picture of 3,000 of my closest friends. Thanks.
Great, thank you very much, Liza. I also noticed that this microphone, I think you might have put a sticker on here. It's got 2 H's here.
Yes.
So let's see if there are any questions. Can you pass this back?
So in the gamma gamma BB channel, you consider 2 separate B jet. Would you increase any sensitivity if you also consider the case where the 2 B jet merge? Because in CMS we saw that Higgs to charm actually gain a lot of sensitivity by adding that.
I think that would be a little bit marginal in this case. So this has helped a lot in single Higgs measurements in cases where you have just a lot of statistics available. At this point, we're still super stats limited, so I don't know if you would have any population in the tails like that. One case where that would help a lot, though, is when we search for resonant production of Higgs to gamma gamma BB. So you've got some intermediate, resonance that you're looking for. A new scalar, for example, something heavy decaying to 2 Higgses, which then decay to gamma gamma and BB. In that case, having the boosted BB jet reconstruction would be useful.
Thank you.
Questions? Yep.
So I was wondering, could you go back to the plot, although I like that picture, of the projections and the systematics in them, where you had it broken down between experiment and theoretical contributions and the statistical?
Oh, this guy.
Yeah, this one.
Yeah.
So in a lot of these cases, you pointed out that the theory systematics are leading. You didn't elaborate on what component of them is the dominant source. Are these scale uncertainties? Is this parton showers? What ends up mattering here? Because it didn't look like anything other than the scales mattered in the analysis that you showed the table from earlier.
Yes, so that is a little bit misleading because that is specifically the Higgs cross-section calculation, and we currently have a huge uncertainty on that. So the theorists who do the calculations of the Higgs cross-sections have recently added considerations where the top mass is finite, which is great, but this has brought a very large uncertainty on the scale. This is something I understand they're working on. Now for the single Higgs ones, I am unsure. I would have to check. This is also from the previous round of projections, so hopefully
Okay.
This is also something that's getting better.
Cool, thanks.
Yes, hi. Nice talk, thank you.
Thanks.
So if you do happen to see Higgs bosons sooner, it might be because of beyond the standard model physics.
It's definitely because of
And,
yeah.
and that's, motivates trying to look right away because it would be so sensitive.
Yeah.
And what BSM physics is you do think is most exciting to look for or most sensitive?
Ooh. Yeah, so I'm really holding out for there being more Higgs bosons or more Higgs boson-like things, right? I mean, it seems super weird that there would only be one. Everything else that we've seen, there's, generations. So we have I didn't share it today because I only had an hour, but we have a wide search program for looking for new scalars decaying to Higgs, both the case where both Higgs are standard model. We also have the case where you have one new heavy scalar, one slightly heavy new scalar, and then one standard model Higgs boson. So here you're still benefiting from using the known Higgs that we have found as a standard candle, but looking for these new particles. Hopefully,
So
nothing yet.
You'd see a signal sooner.
Fingers crossed. Yeah.
Any other questions?
Could you go back to slide 84, I think? Yeah, I just didn't have enough time to digest this slide. So how do I read these and how do I read them together?
Which one should we be looking at?
The right one first. I didn't quite understand.
Okay, right one first?
Yeah.
Okay, so here, this is a projection to the HLHC of our current BB tau tau search. So we are a factor of 3-ish away from the standard model. We're setting limits on Higgs to BB tau tau production of about 3 times the standard model. If you project that analysis forward to the HLHC dataset, so this is a factor of 20 more data, the blue dotted line is exactly where we are at just with that analysis performance, right? So assuming the baseline systematic scenario, which we've decided is the one that we want to compare between experiments, you get about 3.4 sigma. If you have no systematic uncertainties, of course, you're going to have a higher significance. If you assume that the systematics uncertainties stay like what they are right now, this is pessimistic, less significance. Now, you can take this projection, so the blue dotted line is just directly that analysis. If you decrease the B tagging efficiency, so you say we get worse at finding B jets, this is a possibility, given the pileup and everything at the HLHC, the significance would get worse. If you increase the B tagging efficiency, your significance gets better. Now here we've made the assumption that we can design a B tagging algorithm that would be able to increase the significance while keeping the same light and C jet rejection that we have right now. This is, you might say it's kind of a big assumption. It's a challenge to continue to keep the same background rejection while increasing the signal efficiency. But with the new algorithm that we have available for the Run 3 data, we can use the 82% working point. So this is 82% efficiency at finding B jets. And it has the same background rejection. So we believe that, at least that point is already doable.
Yes. Okay. Did any of that feed into the left plot?
No.
Okay.
So the left plot is to try to give you an idea of what we can do with improvements to analysis techniques and object reconstruction. So this plot is mostly just more data. This plot, this is all real. So the orange point is the limit that we were able to set on the Higgs signal strength using a quarter of the Run 2 data set in the BB tau tau channel. The blue point is the limit we're able to set on the signal strength using the full Run 2 data set. So that's the 140 inverse femtobarns. And then the green point is a reanalysis using the full Run 2 data. Now, you can project that forward. So you can say, I've got the orange analysis that we started with. If you did that analysis, but you had 4 times as much data, you would get to the end of the orange line. But in fact, we're beating that by quite a lot. When we actually analyzed those data, we had better reconstruction, better analysis techniques. The comparison that you can take between the blue and the green points is that if you project the blue point forward to where you're getting the same expected limit as we get in the green analysis, it would have taken an additional 60 inverse femtobarns. So more than a third of the, yeah.
Yep, makes more sense now. Thanks.
Okay. This is something that we're trying to refine, the messaging on all of this. So yeah, the questions are helpful. Thank you.
Great. Any last quick questions? If not, let's thank Liza again.